Hi, welcome to the Electronics Lab. In this video, I'm going to talk about Kirchhoff's voltage law. Kirchhoff's voltage law says that around any closed electrical loop, the sum of the voltage rises, that's what this is indicating, the sum of the voltage rises equals the sum of the voltage drops. Another way to put that is that the sum of the voltages around the loop is equal to 0. And that's because some of the voltages will be rises, so positive, some of the voltages will be drops, so negative. So Kirchhoff's voltage law on a simple circuit looks something like this. Each one of these rectangles represents some circuit element. It could be a resistor, it could be a voltage source, it could be a current source. They will all have a voltage drop across them. And we need to designate which way that voltage is going to be. So I'm going to draw that with the voltages all the same polarity. That doesn't mean they're actually the same polarity, but what this allows me to do is say that V1 plus V2 plus V3 plus, I should call that V4, plus V4 is equal to 0. And in order for that to be true, at least one of these has to be positive and at least one of them has to be negative in order to add all these up to get 0. And that's fine because some of these will be voltage sources and some of them will be resistors, for example. So a voltage source may be a voltage rise, but then as current's going through, let's say V2 here, there's going to be a drop across V2, so that'll be a voltage drop. So the sum of the voltage rises equals the sum of the voltage drops. That's another way that I could have done it. And the loop doesn't have to be a simple loop like this, where there's only one loop in the circuit. It could be something more complicated like this. And no matter what loop I choose in this circuit, as long as I come back to the same point that I started with, the sum of all those voltages will be 0. So if I choose this loop, I would consider V1, V2, and V3. If I choose this loop, I'm going to have V3, V4, and V5. So maybe I would start at this point, go through V3, add V3, V4, and V5, and I'm back to the beginning, so the sum of those voltages has to be 0. Same thing in this loop. Maybe I'll start at this point, V6 plus V5, or maybe it's minus V5, depending on which way the polarity is defined, brings me back to 0. It could also, doesn't have to be an inner loop, it could be this outer loop here. So if I start at this point here, I've got V1, V2, V4, and V6. Add those together, and that should bring me back to 0. When I'll do some examples where I put some actual components in there, and then the polarities will start to make sense, and you will see whether you're actually adding or subtracting voltages as you go around a loop. The KVL loop is kind of analogous to going for a hike on a mountain, and starting in the parking lot, going up a path, climbing the mountain, coming down a different path, and ending back at the parking lot. Your elevation, which can be analogous to the voltage, is going to be the exact same when you finish as when you started. So all of those elevation rises will be equal to all of the elevation drops, just like all the voltage rises are equal to all the voltage drops in Kirchhoff's voltage law. So if I have a mountain here, and excuse my drawing, I'm not an artist, and you start at this point here, here's the parking lot, and you take this path that takes you on the mountain, and maybe you go around the other side of the mountain, and then up to the top. I'm going to use a different color here for the trip down, and let's say I start by going down the other side of the mountain and come around here, and this brings me back to the parking lot. That elevation rise that I had on the blue path is going to be exactly equal to the elevation fall that I had when I'm coming back to the parking lot. And that's a really good analogy for the way Kirchhoff's voltage law works. All the voltage rises have to be equal to the voltage drops. Okay, I'm going to do a couple of real circuits with some real number examples. So if I have a 12-volt source here, the current's going to go through the circuit this way, and the voltages across the resistors are going to look like this. So as we go in a loop in this direction, we'll have a voltage rise from the 12-volt source and voltage drops across each one of these resistors to bring us back to the beginning. So let's say this is 6 volts. And this is 3 volts. The voltage across this resistor has to make Kirchhoff's voltage law true. So since the voltage rise is 12 volts, my voltage drops must also be 12 volts. So that means that this one must also be 3 volts. And like I said earlier, KVL applies not only to simple circuits like this, but to circuits with multiple loops in them. I'm going to arbitrarily pick some voltages, but it's not totally arbitrary because Kirchoff's voltage law has to apply on every loop. So does KVL apply in this loop? Well, if I start in this point, I have a 15-volt rise, a 3-volt drop, a 10-volt drop, a 2-volt drop, and I'm back to the beginning. 15-volt rise, 3 plus 10 plus 2 is 15, and so my voltage drops are equal to my voltage rise. Okay, let's consider this outer loop here. Again, I'm going to start at this point and go around the loop, look at all the rises and the drops. Well, I've got 15-volt rise, 3-volt drop, 3-volt drop, 3-volt drop, 4-volt drop, 2-volt drop. That's 3 plus 3 plus 3 is 9, plus 4 is 13, plus 2 is 15. 15-volt rise and 15-volt drops. Now I can also consider this loop here. Even though there is no voltage source there, the KVL, Kirchoff's voltage law, should still hold true for this circuit here. So if I start it, I can start at any arbitrary point. I'm not going to start at this point this time. I'm going to start here. So here I've got a 4-volt drop, 10-volt rise, 3-volt drop, 3-volt drop. So 10-volt rise and 3 plus 3 plus 4 equals 10-volt drop. So KVL also works on this loop here. It's going to work on every loop in any closed loop in an electrical circuit. And that's it. You're going to find that KVL applies in all sorts of circuits that you need to look at, whether they're just electrical circuits like this or electronic circuits with transistors and diodes. The loops in all of those circuits are going to follow Kirchoff's voltage law. So it's a really good one to keep in your mind. The good news is it's a fairly simple one to understand. And once you've applied it a few times, it's going to become second nature to use in any circuit that you encounter. All right, well, I appreciate you watching. I appreciate you staying tuned to this video. I'll see you in the next one.